Welcome back, everyone, for another deep dive. This time, we're going to be looking at how transformers learn.
Oh yeah, this is going to be a good one.
These are the powerhouses behind those large language models everyone's talking about these days.
Exactly.
We'll be exploring a research paper titled Emergence of Abstractions, Concept Encoding and Decoding Mechanism for In-Context Learning in Transformers.
Okay.
And this paper, it gives us some pretty cool insights into the inner workings of these transformers,
Yeah, it really digs deep into how they learn.
especially when it comes to in-context learning, or ICL for short.
ICL, that's where it gets interesting.
Right. That's where they can adapt to new tasks without needing that explicit retraining.
Yeah, it's like they're picking up new skills on the fly, which is incredible when you think about it.
Absolutely.
Right.
So how does this research paper explain how ICL actually works?
Well, they approach it from this Bayesian framework.
Bayesian, okay.
So basically, the transformer figures out the underlying concept or connection between inputs and outputs in the examples they're given.
And they call this hidden connection the latent variable.
Okay, the latent variable.
Right. And then once the transformer kind of grasps that latent variable,
Yeah.
it can then apply that understanding to solve new problems that are related to that concept.
So it's like it figures out the underlying rule and then applies it to a similar situation.
Exactly. That's a great way to put it.
Could you maybe give us a real-world example of how this Bayesian approach works in a language model?
Sure. Let's say you're using a language model and you ask it to translate some sentences from English to French.
Okay, yeah.
Even if the model hasn't been specifically trained on those exact sentences, it can use the examples you've given
Right.
to kind of figure out the rules of grammar and vocabulary translation.
Yeah.
It's using that Bayesian framework to kind of deduce the latent variable in this case, which would be the concept of translation.
Right, so it's going beyond just memorizing phrases.
Absolutely.
Yeah.
It's about understanding that deeper connection between the two languages.
I like that.
Right. It's really remarkable.
So we've got this Bayesian framework,
Yeah.
but to really understand how this whole ICL process works, the researchers propose this two-stage mechanism called concept encoding decoding,
Right.
which they observed in both small and large transformer models.
Yep, across the board.
Okay, so tell me more about these encoding and decoding stages.
So picture it this way.
Okay.
During the concept encoding phase, the transformer is creating these distinct representations for different concepts.
Yeah.
It's almost like the model is developing its own internal concept dictionary,
Right, so each word or each concept gets its own entry.
Exactly.
Right.
And each entry represents a specific concept.
Like building blocks of understanding.
Exactly. Perfect analogy.
I like it. So what happens in the concept decoding stage?
Well, during this stage, the transformer develops these specific algorithms that are linked to each of those encoded concepts. It's like having a toolbox with all sorts of tools.
Okay.
And each tool corresponds to a specific concept. So then the transformer can select the right tool or algorithm based on its understanding of the task at hand.
So it's using the right tool for the right job.
Precisely.
It's amazing how transformers are creating this whole internal structure for understanding and applying concepts,
Yeah, it's really fascinating.
So to actually study how this concept and decoding works in practice,
Right.
the researchers, they used a simplified task. What did they use?
They used a sparse linear regression task.
Okay.
It's a pretty classic machine learning problem where you're basically trying to find the best line that fits a set of data points.
Okay, so fitting a line to data.
Yeah, but they made it a bit more complex by introducing different bases.
Bases, what are those?
They're basically different underlying rules or equations that determine how the data points are related.
So it adds a layer of complexity.
Yeah, exactly. They wanted to see how the transformer would adapt to these different rules.
That makes sense. So what did they find when they did this?
Well, they found something pretty remarkable, actually.
Yeah. Ooh. I like remarkable.
Yeah. So as the transformer learned to solve this task, it started grouping representations of similar tasks together.
Okay.
Visually, it looked like it was creating separate clusters for each base or underlying rule it had figured out.
So it's not just solving the problem, it's organizing its understanding as it goes.
Yeah, exactly. It was really cool to see.
So the transformer is like visually grouping similar problems together.
Yeah, it's like it's creating its own little categories.
Wow. So how did they know that these separate representations were actually linked to how well the transformer performed?
That's a great question. So to confirm this, They used a technique called causal analysis.
Causal analysis, okay.
And what they did was they made some very subtle adjustments or patches to the model's activations.
Okay, so they're tweaking things a bit.
Yeah, they were basically making it easier or harder for the model to infer the correct concept.
So they're kind of like manipulating the concept representation.
Exactly, and they wanted to see if that had a direct impact on performance.
So what happened when they did that?
Well, the results were pretty clear.
Go on.
When they made it easier for the model to encode the concept correctly, its performance improved significantly.
Oh, wow.
But then when they hindered that concept inference, the performance dropped.
I see. So there's a clear link.
Yeah, it really demonstrated this cause and effect relationship between concept encoding and how well the transformer learned the task.
That's pretty compelling evidence.
Right.
But this was all with that simplified task.
Yeah.
Did they test this idea on any more complex problems?
Absolutely, they did.
Okay, great. So tell me about that.
Yeah, they wanted to see how this would hold up in more real-world scenarios.
Right.
So they tested it on tasks involving natural language processing and arithmetic.
Okay, so more complex stuff.
Exactly.
What kind of tasks specifically?
For language, they used part-of-speech tagging.
Part-of-speech tagging.
Where the model had to identify like the grammatical role of words in a sentence.
So is that like figuring out if a word is a noun or a verb or an adjective?
Exactly, yeah. And for arithmetic, they use something called bitwise arithmetic.
Bitwise arithmetic.
Yeah, it involves logical operations on binary numbers.
Okay, so that sounds a lot more complex.
It is, yeah. It requires a deeper understanding of both language structure and those logical operations.
So they're really challenging the transformer with these tasks.
Yeah, they wanted to see if that concept encoding decoding still held up.
And what did they find?
Well, it was pretty interesting.
Okay, tell me more.
The transformers, they were really good at encoding those commonly encountered concepts.
Okay, so like the basics.
Yeah, exactly. For example, in the language task, they accurately encoded words like noun or and.
Okay, those are pretty fundamental.
Right. And in those arithmetic tasks, concepts like and or were really easy for them to grasp.
Makes sense. Those are like the building blocks.
Yeah, like the foundation.
So did they struggle with any concepts?
Yeah, they weren't quite as accurate with those less frequently encountered concepts.
Okay, so the more rare stuff.
Exactly. And this suggests that how often a concept appears during training, it can really influence how well the transformer encodes it.
So it's like anything else, practice makes perfect.
Yeah, the more exposure they get, the better they understand it.
So this could be a reason why transformers are sometimes amazing at some tasks,
Right.
but struggle with others.
Exactly. If they haven't encountered a concept enough, it's harder for them to form that clear representation.
Right. It's like trying to solve a complex equation without knowing basic algebra.
Perfect analogy.
So they've got this idea of a concept dictionary, but how do they actually measure how well a transformer understands a particular concept?
So to do this, they developed a metric called the Concept Decodability Score.
Okay, concept decodability.
Or CD score for short.
TD score, got it.
And this basically measures how easily a concept can be decoded.
Decoded.
Yeah, from the transformer's representations. So a high CD score means there's a clear and distinct representation, while a low score suggests it's a bit fuzzier, you know.
Like a blurry picture versus a clear one.
Exactly. A high CD score means the concept is well defined in that concept dictionary.
Right.
So it's easier for the transformer to apply it to different tasks.
So what did they find when they started using the CD score?
Okay, so this was really cool.
Tell me.
The CD score directly predicted how well the transformer performed on those ICL tasks.
Wow, really?
Yeah, and this was across different transformer models.
So it didn't matter how big or complex the model was?
Nope. It was all about the clarity of those internal concept representations.
So a clear concept dictionary equals better performance.
Yeah, basically.
That's fascinating. So they weren't just observing these concept representations, right?
Right.
They actually tried to manipulate them or improve them, didn't they?
They did. They wanted to see if they could influence those representations and, in turn, the performance.
Okay, so what did they do?
Well, they used a couple of different techniques like fine-tuning and prompting.
Fine-tuning and prompting. Okay.
To see how those affected the concept encoding.
That makes sense.
So let's start with fine-tuning.
Okay, so what did they do with fine-tuning?
They focused on fine-tuning the early layers of the transformer.
Okay, early layers. Okay.
These are the layers that are responsible for that concept encoding.
So they're like the foundation.
Exactly. By fine-tuning those early layers, they were essentially helping the model organize its concept dictionary more effectively.
So they're making sure the foundation is strong.
Exactly.
And what was the outcome of this targeted fine-tuning?
Well, they saw some pretty significant improvements in performance.
Significant improvement.
Especially on those ICL tasks after they fine-tune those early layers.
So it really highlights how crucial those early stages are for the Transformers learning.
Yeah, that's where those concept representations are formed, so it makes sense.
Right. It all comes back to that strong foundation.
Absolutely.
And what about prompting? How did they use that to influence concept encoding?
So with prompting, they experimented with providing explicit concept labels.
Explicit concept labels, what does that mean?
Like if they were presenting an arithmetic problem, they would explicitly state, this is an example of addition.
Oh, so they're basically telling the Transformer what the concept is.
Exactly. And this added context, it actually helped improve both performance and those CD scores.
So it's like giving the model a little hint.
Yeah, and it reinforces that concept association.
It makes it more clear.
Precisely.
But I remember them cautioning against over-reliance on prompting, right?
They did, yeah.
What was the issue there?
Well, while prompting can be helpful, they stressed that it's important to find a balance.
Okay.
If you rely too much on prompting, the model might start to exploit superficial patterns in the data without really understanding the concept itself.
So it's like memorizing answers without actually understanding the material.
Yeah, that's a great way to put it. You want the model to truly understand and generalize.
Right, not just regurgitate what it's been told.
Yeah.
This research is really shedding light on how Transformers learn, especially with this concept dictionary idea.
Yeah, it's pretty mind-blowing when you think about it.
It really is, and it seems like this knowledge could lead to some really exciting advancements in AI.
Oh, absolutely. It opens up a whole new world of possibilities.
So where do we go from here? What are the implications of all this?
I think it changes how we view AI, you know?
Yeah, it's not just about crunching numbers and patterns anymore.
Exactly. This research suggests that AI, especially transformers, are developing something like understanding.
It's like they're building these mental models of the world.
Right, just like we do. And this understanding, it opens up so many possibilities for how we develop AI going forward.
So instead of just feeding AI massive data sets, we need to think more carefully about how that data is structured.
Absolutely.
And presented.
Yeah, it's about helping them form those concepts.
Right, so it's about creating a learning environment where AI can develop this robust understanding of concepts and how they relate to each other. Yes. And this research also highlighted how important it is to fine-tune those early layers.
Oh, yeah, the ones responsible for concept encoding.
Exactly, because by fine-tuning those layers, we can essentially refine how the concept dictionary is organized.
Right. Making it more efficient, more accurate.
And then prompting, used strategically, can really strengthen those concept associations.
It's like giving the model a little nudge in the right direction.
Yeah, but as we talked about before, it's all about balance.
Oh, yeah.
We don't want the model to become too dependent on those explicit cues.
Right, because then they might miss out on developing that true understanding.
It's like the difference between memorizing facts for a test versus actually understanding the underlying principles.
Exactly. You want the model to be able to apply its knowledge to new situations.
Right, not just repeat what it's been told.
Exactly.
This research has given us so much to think about.
It really has.
I mean, if transformers are learning by forming these distinct representations for concepts, could we teach them even more complex reasoning skills?
Ooh, that's a great question.
Like by strategically shaping those representations.
Yeah, that's something researchers are really diving into right now.
And if we can figure out how to influence the formation and refinement of those concept dictionaries...
Who knows what AI will be capable of?
It's like we're not just building machines anymore. It's almost like we're shaping minds.
It really is. And that brings a whole new dimension to the future of AI, both the potential and the responsibility.
Well, this deep dive has certainly been an eye-opener.
It has.
We've learned that transformers are more than just pattern-matching machines.
They're developing these internal representations of concepts, which allows them to learn and adapt in really remarkable ways.
Absolutely. And as we continue to explore this field, it's important to remember that AI is a reflection of us, of our own creativity and ingenuity.
It really is. The future of AI depends on the choices we make today.
That's a powerful thought to leave our listeners with.
It is.
Thank you, everyone, for joining us on this journey into the world of transformer learning.
Thanks for having me.
We hope it sparked your curiosity and inspired you to think about the future of AI.
It's a fascinating field, that's for sure.
And until next time, keep those minds curious.